Okay, I think we are now live. I'm just gonna pull up my calculus notes. It has been quite some time. I think it's been like almost 2 weeks. My computer had some stability issues, and so took a bit debugging. And then someone was in town last week, so did not able to didn't stream last week. So. But now we're back on the horse. Hopefully my calculus knowledge has not completely gone down the drain. And if not, this would be, a good time review. Or to review. Bring it back to my memory. Long gone. Okay, so... I think we'll probably just go start right on in. Hopefully we can get completed pretty quickly, or Anki completed pretty quickly, and then we'll shoot for working through as much as the test as we can. I'd like to be able to get through this test fairly quickly. I know I've said that a few times before, but we'll see if this time is the charm. Okay. Sweet. So let's go ahead and we'll zoom in a bit. Yeah, seems reasonable. Okay. So the first one here is, what is the mean value theorem in calculus? I believe this is the I believe this is that for a given... Oh, actually. So my guess is that it's the thing with the tangent and cotangent, where if you have a particular conditions met for the function, and you have a cotangent, there exists a cotangent line. There exists the tangent line that is the same as the cotangent line and represents the average between the 2 points, but or average slope between the 2 points. Okay. That if f of x is continuous on a closed interval and differentiable on an open interval, then there is a point. Okay, perfect. I think I'm going to send that one back through. Okay. This one is when you're taking the limit, you can apply the same product rules. Same for roots. Dx over x, or sorry, d over dx. I still don't know that one, so I'm going to send that one through. Indefinite integrals represent the set of all families, the family of all functions that the broader set of functions will integrate to. And because it, let's see, I need to be able to say that better. It makes sense, but it's clear that it's not a great definition. Indefinite integral is the set or the family of functions it's the family of functions that share everything besides the constant, because the constant falls off when you integrate something. the indefinite integral represents the family of functions that are the same, where only the constant would vary. Okay, that's it right there. So indefinite integral is the family of functions that are the same the family of functions that are the same outside of a varying constant. And definite integrals are where you take like have two antiderivatives and you take like an actual volume under the curve. Oh, let's see. Yep, family of antiderivatives. Yep. Okay. Open intervals are non-inclusive. Closed intervals are inclusive. Okay. So for it to be continuous at a point, say for a given x has to exist. The derivative of x has to exist, and if we plug in x to the derivative we got, then that also exists. Okay, no, that's not it. Okay, so when we take the limit to that point, it exists, and the limit to that point is the same thing as okay, so for a given x is defined. If we take the limit to x, it exists, and if we substitute x in for the formula and take the limit of x, they are equivalent. Okay, well, piecewise function is like a conditional function. I don't know that one, and we'll send that one through. I'm just going to learn it when I have the full context of it in the exam. Okay, concept of the slope of the tangent line. So this is the instantaneous slope. So for a given portion of a function, this is the slope at that point. The limit laws. The limit laws enable us, or sort of give us explicit rules for how to derive a limit from a function. They are the like, if you knew math, the limit laws, or knew basic like operations, what is it, PEMDAS, or like if you knew basic like algebraic operations, then it's not surprising to you the limit laws, but I think they're made explicit so because outside of it being explicit, we wouldn't know what they were, right? Because limits are different, so we need to be explicit about them if we want to like have them be in mathematics, right? Okay, in calculus, how do you find the vertical asymptote for rational functions? So a rational function is where you have a fraction. That may not be entirely the case, because oh, sorry. No. Rational functions are where it's not an irrational function. Irrational functions are typically where you have a fraction. I need to figure out, I think rational numbers are ones in which that are ones that don't go on forever. I think I did talk about wanting to do some number theory stuff, but I think I need to do that sooner rather than later. Okay. Let's see. So rational. Actually, let's just look into that real quick. A rational and irrational number. My hypothesis is that irrationals are infinite. Ah, okay. So it's actually their ability to be expressed as a fraction. Rational numbers can be expressed as a fraction of two integers, while irrational numbers cannot. Essentially, rational numbers can be written as a ratio Oh, okay. So rational numbers do include forever numbers. Irrational numbers are like. Oh, interesting. So rationals can repeat, whereas irrational numbers, non-terminating, non-repeating. Interesting. So I was definitely wrong. Interesting. Okay. So rational numbers, repeating decimals, terminating decimals, and integers. And they can be expressed as a fraction of two integers, whereas irrational numbers cannot be expressed as a fraction of two integers. Non-terminating, non-repeating square roots. Okay. I like that. That's good to know. I am going to write that down to create card for that, but we won't quite yet. Okay. So for rational functions, this is actually one that can be expressed as a fraction. So I'm gonna go back to the other. Go back to the other side. The vertical asymptote for a function, for a rational function. Okay, so I believe it's the case that okay, so for a vertical asymptote, the lower integer would get arbitrarily small, and then which would make the resulting function arbitrarily large, the lower integer. The denominator would get arbitrarily small, and the resulting value of the function, fraction, would get arbitrarily large. So like my intuition says we just need to find that thing, or find the resulting denominator find the input that causes the denominator to arbitrarily approach 0. Because that's when we get huge numbers resulting. So, but that's not really formalized, and I'm pretty sure this is a formalized answer. Identify values of x where the function is undefined, typically where the denominator of a rational function is 0. Then check if the function approaches positive infinity or negative infinity as x approaches that value from the left to right. Okay, so the only thing that I missed was that a good hack would be to find where values of x where the function is undefined, because in those instances, as we approach either side, we're probably going to have that like infinite. Actually, that's incorrect. We could possibly have that. Well, okay, no. So I think I don't think that's exactly the case, because we could have a removable discontinuity here, right? In our situation with like x squared minus 4 over x plus, x minus 2, we'll say, where that's a removable discontinuity that doesn't involve infinities. That's a lie. Okay, no, that one does involve infinities, because as the result gets arbitrarily close to 0 from the negative or positive side, we approach negative and positive infinity. Okay, so we just gotta remember where it's undefined, typically where the function, where values of x where the function is undefined, and then where it approaches. Okay, so it looks like it is the rule of thumb. Okay, an antiderivative is the result of if you're taking an integral of a function, and it's done by the inverse power rule. Antiderivative. Yep. Okay. I don't know the chain rule yet. This is a piecewise function. Vertical, horizontal, and oblique. I don't know. Oblique. Okay. Yep. Okay. This is a mean value theorem. So we need to be continuous on a closed loop, or sorry, closed interval, and derivable on a open interval. Differentiable. Yeah, that's a better way to say. Okay, syntactic difference. Okay, closed is square brackets. Product sum, exponent, root, constant, plus or minus, or sorry, sum or subtraction. Okay. D over dx. Okay, so if I'm recalling correctly, the slanted asymptotes are all about the relationship and the exponent size of, or exponents above in the numerator, and then like the ratio of exponents in the numerator and the denominator. Divide the numerator by the denominator using polynomial long division. If the degree of the numerator is exactly 1 higher than the denominator, the quotient is the slant asymptote. This describes the functions and behavior as x approaches negative or positive infinity. Okay, so we're going to have to divide the numerator by the denominator, and then if the degree of the numerator is exactly 1 higher than the denominator, the quotient is the slant asymptote. So I do have a question. So first it describes that we're going to be dividing the numerator by the denominator using polynomial long division. So if the results of that, is that what we're saying? That the degree of the numerator is exactly 1 higher than the denominator? So I'm going to check that out. This is an Anki card. I'm wondering about whether this is an Anki card. I'm wondering about whether. Oh, is it not going? It doesn't seem to be working. Okay, I guess I'll just type it out. Oops. I am wondering. Difference in degrees between the numerator and the denominator. Denominator. After we use polynomial long division, or before. Oh, okay. Okay, so this isn't the structure of the question isn't great, because it kind of gives me the wrong vibe, or the wrong could you restate the Anki answer? Anki answer to reflect that. Perfect. Perfect, perfect. Okay. Actually gonna have to pop that in here. Doop. Okay. Sweet. Okay, so we'll send that one back through, but now I feel quite confident. And one thing with the learning like this, it may seem like I'm taking a long time for some of these ideas, but I recognized, and this is actually a really important sort of metacognitive habit for learning, is to recognize when you don't understand something. Most people, most students are unable to recognize when they don't understand something. And this is the case because typical methods in studying require, like the Feynman technique, require you to teach it to determine whether you know it, right? And so if someone can't reliably ascertain their knowledge without teaching it, then it's clear that they don't understand it, right? Deeply. And so, like finding areas where it's unclear, or just being able to recognize that, is a really powerful and important, really powerful and important to be able to do. Okay, so. Okay, sweet. So I think now we'll just keep going. Okay, 3 conditions for a function to be continuous at a point. So x has to exist, or has to be defined. As we approach x, or for a given x, the function has to be defined. As we approach x, actually I think I'll use c. So for a given variable c, no, I will use x. For a given variable x, it has to be defined at that point. If as we approach x in the limit, then it has to be defined as well, and then x has to be equal to the limit of x. Yep. Okay. Limit lob. So we just are able to like use normal mathematics or algebraic like mathematics for that. Okay, this is a derivative of a derivative. It shows us the rate of change of the rate of change. Or yeah. Derivatives. So this is the in a calculus how do derivatives and integrals relate. This is the I don't know. They call it the grand fundamental theory of. I forgot exactly what they call it, but like the fundamental theory of calculus is that derivatives and integrals are inverse functions, or inverse processes. That's a better way of putting it. A jump discontinuity. This is one that can't be removed, and usually like entirely misses a point. I'm not sure if this includes infinities. Is that when we're approaching from different points, there's a discontinuity. So we'll send this one through again. How do you find horizontal asymptotes for rational functions? Figure out, typically this is when you have a fractional or a fraction in your function, and these occur when the denominator arbitrarily approaches 0 from the negative and the positive. Oh, I don't. Okay, I think Leibniz is close to, or Leibniz is the prime, and then Lagrange I think is d over dx, dy over dx. Okay, Lagrange notation uses the prime marks. Okay, so I was totally flipped. So Leibniz notation is dy over dx. Shows the derivatives of ratio of changes. Lagrange notation, which is like similar to Newton's notation. I think Newton uses dots instead of prime, like the little apostrophes, I guess. Okay, send that one through again. Okay, so So the secant line for like 2 given points, or given 2 points on a secant line. Yeah, I guess that's a reasonable way to put it. The mean value theorem says that there is a tangent line that is the average between those 2 points that is parallel to the secant line. Beepity beep beep beep. Parallel. Yep. Okay. Okay, vertical asymptotes. So first you have to determine if the numerator is 1. I think it's, the numerator is 1 degree higher than the denominator. The denominator, oh, wait. Oh, this is the vertical asymptotes. Okay, for some reason I was thinking of the oblique ones. So I'm pretty sure we already answered that earlier. Okay, Leibniz notation. This is the dy over dx. Oh, shoot. Oh, no, that's correct. Lagrange notation is the primes. Yep. Okay. Why is it the case that vertical asymptotes can be found through considering the denominator? Because as we arbitrarily approach 0, we find the vertical asymptote. The syntax for resulting derivative of f of x. So f prime of x, or dy over dx, like, so the Lagrange, or sorry, the Leibniz notation. A dy over dx, yep, okay. And okay. How's the indefinite integral of f of x dx expressed in terms of antiderivatives in calculus? Okay, I think, oh, sorry. Okay, so this would be f of x plus c. F of x plus c. Okay, I was correct. Yep. The summation operator in mathematics. Oh, it's this little e thing. How do you find slanted asymptotes? So this is when the numerator is 1 degree higher. If the degree of the numerator is exactly 1 higher than the denominator. Okay. So, and then we'll perform polynomial long division, and then the resulting quotient is what occurs as x arbitrarily approaches negative or positive infinity. Okay, so we'll just go back over for that one. This is where we have a sudden jump if we take a limit of a given value from both sides. Okay, Leibniz is dy over dx, Lagrange is f prime. Check if the power is 1 higher than the lower, and then do a resulting polynomial long division, which I need to write down because I haven't done that since, like, probably, yeah, it's been at least maybe probably close to 10 years since I've done something like that. So polynomial long division. Okay. Perfect. Nice. Okay, I do want to add, we're going to zoom in here. Is the difference between rational and irrational numbers in mathematics. Do polynomial long division. I'm actually gonna do this one later. Go on. Oh, we got a whole lot of tabs here. We'll just keep closing. Okay. This is the same one there. Okay. I think we are chilling. Okay. So I think we'll go back to the bottom here. And then we'll just kind of keep going through. I'm gonna get a refill on my soda real quick, and I'll be back. Okay, sweet. Da-da-da-da-da. So yeah, I guess we'll just keep going through. So yeah, we'll just keep them 1 and 2. Okay, we don't have a vertical asymptote because there's no denominator. And then for identifying horizontal asymptote, oh, I think when I was going through, I skipped through. I mistook the horizontal for the vertical, and so I skipped through the vertical or the horizontal one, thinking it was the vertical one. So I think we'll just find this real quick because I'm not recalling how to find a vertical a horizontal asymptote. But let's see if we can figure it out real quick. As our input gets arbitrarily large, we're going to have the same output. Or sorry, we're getting close to the same output. So when it's like inversely the case for the, so I guess we'll make this clear. Excalibur. Okay, so for vertical asymptotes, they're like this, and then anyway, we got like this. You got this vertical asymptote here in the beautiful orange color. Okay, so yes. Okay, so as we approach like this one, as x approaches this, then we get here, but our horizontal asymptote is as we approach, or sorry, as we approach infinity. Let's see. I guess we could. I don't know if they. Okay, we'll just pretend this will work. So these look actually like quite similar, but we'll just say okay. Yeah, I'm not sure. Okay, yeah, I think we'll just go ahead and ask. How do I find horizontal asymptotes? Okay. Compare if the degree of the numerator is less than the degree of the denominator. Good to know. Okay. These are great. Okay. I'm actually going to look at my card. This is a really good explanation, and so I don't want I want to make sure that this is captured here. Okay, so we'll go to browse, go to Dex, we'll go to calculus and browse, horizontal. No way I have that many cards that say horizontal in it. Oh, okay, this says every card. Still seems odd. Oh, horizontal line. Okay, whatever. Yeah, I would not have guessed that I have 79 cards in my deck that all say horizontal. Okay, in calculus, what are, or I guess in my total cards. In calculus, what are the three types of asymptotes for functions? Vertical, horizontal, oblique. Okay. Evaluate the limit. Okay. Find horizontal asymptotes. Evaluate the limit of the function as it approaches. Okay. Okay, so I think I think we're going to replace this because this talks about evaluating the limit. I just want a little bit more meat. Okay, so to find the horizontal, I want to split this here so it's just visually clear. The numerator. Okay. Compare the degrees of the numerator and the denominator. If the numerator's degrees is less than the denominator's, the asymptote is 0. If the degrees are equal, it's the leading coefficient of f and the leading coefficient of g. If the numerator degrees exceed the denominators, no horizontal asymptotes exist, though check for a slant asymptote if the degree is 1. Perfect. Okay. I think the leading coefficient is probably the one with the highest degree. So I just want to make sure of that. But I also want to note there. What is the leading coefficient? In mathematics. And what do you think this would be, algebra? Is the term with the highest degree. Okay, perfect. Yep, that's what I thought. Okay. Okay, perfect. Oops. Okay. Okay, this makes sense because if our degrees are the same between the two, that means that they're going to be growing at the same rate, or rather, not at the same rate because there might be slight differences, but they're going to be growing at the same magnitude. I don't know if that's the correct. Would it be correct in saying that? Man, I am not. This is not working. Okay, I'll have to debug that later. Correct to say that when the degrees are the same, and the denominator. Okay, would it be correct to say that when the degrees are the same denominator, the asymptote is 0 because y equals 0 because as x gets arbitrarily large, y or sorry, the numerator and the denominator grow at the same relative magnitude. Oh, let's see actually. Okay. So when they're the same, that's when we check the highest. We take the value of the leading coefficient. But the numerator's degree is less than the denominator's. The asymptote is 0 because as the denominator, or sorry, as both arbitrarily approach infinity, because I'm still going to ask this question because I want to make sure that magnitude is the right word here. But I'm wanting to know how I would describe the difference in the rate of growth between the numerator and the denominator, or the value of the numerator and the value of the denominator. Because when the numerator is 1 power less than the denominator, then we have the asymptote of y equals 0. And that's because the denominator grows much more quickly than the numerator does. So I want to make sure that is it right to say technically that the magnitude of growth between the denominator is higher. The magnitude of growth of the denominator is higher than that of the numerator. So as they get arbitrarily large, y approaches 0. Magnitude refers to absolute value, size, or vector length, not polynomial degree. When discussing horizontal asymptotes, the key concept is the degree. Yep, okay. Okay, so not a standard term. What is the technical way to describe the difference in growth between the denominator and the numerator? I don't know if I like that. I want to describe, I think in a non-technical context, well, I think it's, if I don't want to be incredibly, well, like, well, I don't know. I think magnitude, I think it's fairly reasonable to describe as the magnitude, because we're describing the size of the rate of growth and how the magnitude is, the size of the rate of growth is higher than than the okay, so we want to be precise. Then we use degree, right? Talk about rate of growth. Asymptotic dominance. Wow, I don't think I was expecting to see the word combination like that today. Okay. Okay, so because there's no so the vertical asymptote is when the numerator is 1 degree larger than the denominator. Nope. That's correct. Denominator, there is no, yeah. Horizontal asymptote, because this occurs in functions where the numerator is one numerator is one degree higher, or if the numerator and denominator degrees match. And because neither of these situations are the case, we don't have a vertical. We don't have horizontal asymptotes. Okay. Okay, I don't like the fact that we're saying we don't have a vertical asymptote because there's no denominator. Is there a better way to we don't have a vertical asymptote here? I am wanting to precise. Okay, this is a good way. Okay. It's bound and continuous. Sorry. Linear and continuous. And remain finite for all x. Remain finite for all finite x with no points where the function approaches negative or positive infinity. There is no vertical asymptote as the function is continuous Okay. As the function is continuous, okay, I don't know how I feel about how we're using different, but I guess the big thing is I don't understand what bounded means here. Vertical asymptote as the function is continuous and for all finite x and remains finite for all finite x, finite for all finite x, x approaching negative or positive infinity. Okay. Feeling good about that. Let's see the feedback. Oh, okay. Okay, so I do need to look into... Okay, because, yeah, that makes sense. Okay, so my description of horizontal asymptotes is only for rational functions. So I need to be here, revise horizontal and vertical asymptote answer. It's like correct in a light, but not actually correct in reality or in all senses. Okay, I think I'm actually going to look into the boundedness of functions. I think I'll just open up a new one here. We'll just go ChatGPT. Reusing. I wish they had better naming schemes here. Okay, I guess we'll just keep for this one. What is the concept, the property of boundedness? Boundedness in the context of functions. Okay, I think we'll probably just hop on boundedness of functions next time, and we'll end here. I think we made some good progress tonight, and I think I have learned a lot about what learning, let's see. I guess not tonight, but I've learned a lot about what it looks like to, or I guess what is, well, okay. I would say that I've learned a lot about the importance and need for preciseness when you're doing like a self-led journey, because we did learn a lot about calculus initially, but if my goal is to be able to pass a test like this, I should just dive into like the test, right? Though I think a general overview was fine at the beginning, because yeah, I feel actually I do feel comfortable with that, because it was like a short video. We just like spent a lot of time on understanding the concepts there. So I think that is fine. Okay. Yeah, I think we're chill. Perfect. Awesome. Well, I will see you guys tomorrow for next session.